So our last topic for this unit is energy in capacitors. So we've just talked about sources of potential. We've talked about capacitors. We've talked about arrays of batteries. We've talked about arrays of capacitors. But we haven't really talked about energy. And the batteries provide our source of energy. Capacitors store charge. Charge is related to energy. But how are they related? Well, assuming we start off here with this uncharged capacitor, and I have this battery basically here. So this positive side built up and this negative side built up. Essentially what you have to picture, and once again, we're actually going to use a conventional current idea. But you can picture it the opposite. So with a conventional current, we actually assume that the positive charges move. And we owe this to the fact that we didn't discover electrons until well after we had been exploring circuits and current. Benjamin Franklin's the one who's credited with conventional current by kind of legend. We don't know if that's actually true, but he did lots of experimentation on electricity and storing charge and so forth. Very, very interesting. I do suggest reading some of his original papers. It's pretty fantastic. But Benjamin Franklin was doing those experiments in like the mid 1700s, you know, think 1776 before that. So that's Benjamin Franklin doing all those scientific experiments in the mid 1700s. So we didn't discover the electron until 1905-ish, 1901 is when J.J. Thomson did his cathode ray experiment. So we had been doing 150 years worth of work in electric circuits before we even discovered the electron. So we do conventional current assuming that it's the positive charges that move. And it's okay, and it actually works. When we get to the circuit, we'll talk a little bit more about why it's okay to still represent current as being positive charges moving, even though we know it's the electrons that are moving. So the other reason we do this is because when we think of test charges with potential, we usually assume that our test charge is positive. So that's the other reason we're going to stick with kind of a conventional current type idea with positive charges moving, because we're going to treat a test charge. So essentially what we can think of is that when I connect a wire here between my uncharged capacitor and my power supply, that what's going to happen is the battery is actually going to have to do work. So it's going to have to move some charge up here to the positive plate, the positive side of the battery, so that that positive charge can flow over to my capacitor. So that's like my little test charge right here. So there is some sort of potential difference for my parallel plate here. I mean, not my parallel, sorry, for the battery. So there's some potential difference in my battery. So you have to lift this positive charge so it can get out essentially across this potential difference, because those positive charges are coming back in through here, coming to the negative side of the battery. So if I want to get it back up here, I'm going to have to essentially lift it. You can almost think about lifting a mass up a hill, because this positive charge wants to stay down. This is low potential for that positive charge. This is high potential. So if I want to get that charge to go from low to high, then I'm going to have to do work. You could think of this with an electron flow by doing the opposite. By having a negative charge up here, you'd have to move that negative charge down to create a negative current in the opposite direction. So it does work no matter which way you look at it. And so we can actually define that our change in potential energy is going to be Q times delta V. So I can gain, by basically doing work here, I'm getting potential energy, a change in potential energy by doing work. So if we assume that this is not a finite charge and that it is an infinitesimally small element of charge, and I replace that and think of it as more of a dq, then I'm only going to get a finite amount of work. So I can define that work as equaling dq times delta V. Now I know that I'm going to end up with the same delta V over here for my capacitor, so that I can relate this potential difference here to the eventual equilibrium potential difference of my capacitor, because we're going to have a transfer of potential. Now, the little tiny bit of potential energy that I get stored here by moving this Q onto my plate, so I get dQs, a positive dQs worth of charge built up on this side, repelling a negative dQs worth of charge over here, that is going to cause a measurable value of delta V. So I'm going to get a du is equal to dq delta V over here. So when I look at an infinitesimally small amount, I get an infinitesimally small amount of delta U, but I have a finite voltage delta V. So with that, the energy is transferred from the battery to the capacitor in order to conserve energy, because energy is conserved. I can then relate essentially the potential difference here to be the potential difference of my capacitor. So the potential difference of the capacitor is going to be Q over C. So I sub that in and I get du is equal to dq times Q over C. So if I do a little rearranging, I get that du is equal to Q dq over C. Now C is a constant. So I can actually pull that out in front and I can get du is equal to 1 over C times Q dq. Since my capacitance is a constant, it's defined by the physical construction of that capacitor. And then if I wanted to find how much charge is being stored, I don't want just one little dq's worth of charge. I want the full dq's worth of charge. So then I'm going to integrate from 0 to u. And over here, I'm going to integrate from 0 to the q, where q is going to be the total amount of charge that's eventually going to be stored. And when you do that, the integral of q is going to be 1/2 of q squared. And so I'm going to get u evaluated from 0 to u. I'm going to get 1 over c times 1/2 of q squared evaluated from 0 to q. So we end up with u equaling, what would that be? Q squared over 2 times c. So that is how much potential energy is stored in a parallel plate capacitor. Now, if this is not a parallel plate capacitor, then this is not going to be the same thing, but you can do the same process with a different distribution if you have a different equation for your potential, because your potential is not going to be Q over C for like a spherical capacitor. Well, no, it is. But you're not going to store the same amount of charge if it's not a parallel plate. So this is not the normal way you see this. We can actually relate it in different ways because we don't normally know Q. So if we use that Q is C times delta V from our definition of capacitance, then you're going to get U is C delta V squared over 2C, which is going to give us U is equal to 1/2 of C times delta V squared. And that is a different formulation for the potential energy of a capacitor. This is really, really nice because remember that for a spring, the potential energy of a spring is 1/2 kx squared, where K is the spring constant. So we have C is our capacitance, and we're going to essentially store energy in a spring by stretching it. We store charge energy in a capacitor by storing it across a difference in potential. So you have a difference in length of the spring. This is a difference in potential. And that capacitor is going to store that energy until it's released, kind of like that spring is going to store energy until it's released. So you could also, if you wanted, rearrange this and get it in terms of Q and delta V. So that version is also possible. So basically, you can using just one of these equations and this guy get any variation of them. There's several different versions of this on your formula sheet. So how does it store charge? Well, it basically stores charge within the actual electric field itself. So we can relate this charge that's being stored in the capacitor to the electric field. So knowing, for example, the capacitance for a parallel plate capacitor is E naught 8 over D, knowing that the potential difference for a parallel plate capacitor is E times D, I can get my potential energy in terms of more the physical characteristics of my capacitor itself. So if I take my potential energy here, let's get rid of this stuff. So if I say that U is equal to 1/2 C, well, C is E naught A over D. Delta V is going to be ED squared. Then you have, let's see, what would this be? One of the D's is going to cancel. So you're going to get E0 over 2, which are our constants, times AD, E squared. And this is the potential energy. This one is specifically for a parallel plate capacitor. Whereas these ones are valid for like any capacitor. It's just what determines your equations is going to be different for different shapes of capacitances. Because you cannot use C equals E naught A over D if this is not a parallel plate. So this part is specifically for a parallel plate. This is really interesting right here because this is the volume of the capacitor. So what this tells you is that if I have a particular capacitor, in this case a parallel plate capacitor, that the stronger the electric field, the more potential energy. I think that kind of makes sense. But then it's also dependent on the volume of the capacitor. So if I have some electric field and it's occupying a larger volume, then I'm also going to get a larger potential energy.